Hi YouTube and happy Tuesday. In tonight's video I just want to talk a little bit about CHIP-8, which is a very fascinating programming language and virtual machine that was first developed for computers running on the RCA COSMAC 1802 processor. I'll just step back for a second and say I'm talking about this because I plan to run CHIP-8 emulators on my Palm OS devices in future videos, as well as several different Casio graphing calculators that I have. And thinking a little bit further, it would be really nice to implement a CHIP-8 emulator on my on my Casio Pocket Viewer once I get around to learning the SDK for that PDA. So without further ado, let's talk a little bit about CHIP-8 using this Wikipedia page. CHIP-8 is an interpreted programming language that was developed by Joseph Weisbecker, who's done a lot of work in the 1802 community, for the COSMAC VIP and Telmac 1800, which both were computers that ran on the 1802. Prior to that, from what I understand, having built a COSMAC ELF myself and having used COSMAC ELF emulators, is that people would write 1802 machine code from scratch, or they'd develop an assembler for 1802 machine code and enter in that code either through switches or through hex key through a 16 key hexadecimal keypad, as you'd see on the COSMAC VIP. But what was great about CHIP-8 is this was a much simpler language to understand, that if I recall correctly, could still be programmed through a hexadecimal keypad, but didn't have the complicated syntax, and just from my prior videos you'd even appreciate the work of figuring out where in memory to place everything from data and code and refer to it all, and change that around. CHIP-8 again was first developed for the 1802 and for 1802 based computers, but since then it's been implemented on all types of different computers, even your washing machine and refrigerator. I kid. That said, it has been made for home computers, microcomputers, graphing calculators, like I'll talk about in the future. There's a version for HP graphing calculators, and now that I think about it, that would make an interesting video. Mobile phones, video game consoles, and it should say here PDAs. There is a Palm Chip or Palm CHIP-8 emulator for Palm OS devices that will come up in the not too distant future. As it says here, the first community used CHIP-8 started in the 1970s on microcomputers. They shared extensions and programs in newsletters. Viper, that would have been before my time, and Dreamer. Later, and this is where it gets interesting, CHIP-8 interpreters started to be created to be implemented on graphing calculators. Notable examples are CHIP-48 and SCHIP for the HP-48. SCHIP is super interesting. That's really an extended CHIP-8 language called SuperChip that has a lot more instructions, and I'll even might just dedicate a video to that. CHIP-8 applications include original games, demos, as well as recreations of popular games from other systems. You can see Pong is kind of a natural fit for this language. It's for very, very low res graphics. Before I go further, I'll show you the Telmac 1800. This is running Space Intercept, I guess kind of like, forget it, I think that's supposed to be like Space Invaders. Some CHIP-8 applications in the public domain with licenses like Creative Commons 0 license. So there's the original CHIP-8 that Weisbecker developed, but later CHIP-8 CHIP-8 versions include extensions like CHIP-10 and high-res CHIP-8, which support a higher resolution than low-res, as I said, 64 by 32, and CHIP-8C and CHIP-8X, which supported limited color. That's kind of cool. As I talked about in a prior video, I have that Casio Prism FX-CG10. I'll see if either I can take the SCHIP FX source code and recompile it for the FX-CG10, or just develop my own super chip SCHIP emulator. Mostly backwards compatible as they're based on the original interpreter, although some repurposed rarely used opcodes for new instructions. Okay, Dream 6800, that's in Australia, so maybe some viewers would have had that or been familiar. If you have, a Dream 6800, or if you have an ETI 660, or if you did and used it, leave that in the comments down below. I'd love to hear that. In 1990, another CHIP-8 interpreter called CHIP-48 was made by Andreas Gustafsson for HP-48 calculators. Then Eric Brintz created another interpreter based on a CHIP-48 called SuperChip, often shortened to SCHIP, SCHIP. It extended the CHIP-8 language with a larger resolution and several additional opcodes meant to make programming easier. Oh, this is very cool. So David Winter had an interpreter, disassembler, and extended technical documentation to spread CHIP-8 like a virus. No, just kidding. On other platforms. It laid out a complete list of undocumented opcodes and features and was distributed across hobbyist forums. I'm hoping that I can develop not just CHIP-8 emulators, but compilers almost, or IDEs for the FX series graphing calculator, where you could type in a CHIP-8 program and then have the type in a CHIP-8 program and then have the compiler convert it to bytecode, to machine code to be or binary file to be executed by an emulator. I'll have to see if it's already possible to import a memo into Palm CHIP-8, or if you need binary files containing the CHIP-8 programs. And I guess in other platforms, I'd probably have to write something up, maybe even something like C Basic for those Casio FX series graphing calculators. CHIP-48 subtly changes semantics of a few of the opcodes, and SCHIP continued to use those new semantics in addition to changing other opcodes. Modern CHIP-8 games are not backwards compatible with the original CHIP-8 interpreter, but as I mentioned, this is an SCHIP emulator, at least for the FX series graphing calculators that I'll show. Now, going through the VM, this is why a lot of people, as a programming exercise, will write up a CHIP-8 emulator. It's a very simple virtual machine. I'll go through the memory, registers, stack, and timers. It was implement 4K systems. The CHIP-8 interpreter occupies 512 bytes of memory space. Most programs begin at memory location 512 and don't access any of the memory below the location. Uppermost 256 bytes reserved for display refresh, 96 bytes below that for call stack, internal use, and other variables. There's no need to avoid the lower 512 bytes of memory, and it's common to store, okay, that's interesting, font data in this low resolution. 16 8-bit data registers named V0 through VF register. You can see in hexadecimal. Doubles as a flag for some instructions, thus it should be avoided. It's the carry flag. Okay. Address register is 12 bits wide. That's interesting, and is used with several opcodes that involve memory operations. The stack is only used to store return addresses when subroutines are called. RCA 1802 version allocated 48 bytes for up to 12 levels of nesting. 2 timers that count down at 60 Hertz. A delay timer and sound timer. When its value is not 0, a beeping sound's made. That's kind of cool. Input, as I thought, was done with I guess within the game is done with a hex keyboard that has 16 keys ranging from 0 to F. 8, 4, 6, and 2 keys are typically used for directional input. 3 opcodes are used to detect input. That is like kind of a challenge with CHIP-8 is you have to read about the program first to know what keys to use for what actions on the game, but I guess that's not too bad. It makes sense, looking at the keypad that you'd have how I should move my hands. 8, 4, 6, and 2 for directional input. 3 opcodes are used to detect input. One skips instruction if the key is pressed. Another does the same if the key is not pressed. And third waits for a key pressed and stores in one of the data registers. Okay, the original CHIP-8 resolution, as I mentioned, is 64 by 32, monochrome display. Graphics are drawn to the screen by drawing sprites, which are 8 pixels wide and 1 to 15 pixels high. They are exclusive ORed with a corresponding screen pixels. I said to flip the color of the corresponding screen pixel, whereas they're set, whereas unset sprite pixels do nothing. Okay. Carry flag is set to 1 if any screen pixels are flipped. That's kind of interesting. From set to unset when a sprite is drawn, and set to 0 otherwise. Ooh, okay. Collision detection, say, if you had some game where like a plane's flying across different size buildings and keeps, like you can blow up a building and the, plane keeps flying lower and lower. There's a game like that for the Sharp PC 1500 that I used to play. CHIP-8 is 35 opcodes, all of which are 2 bytes long and stored big endian. Counting up, but okay, yeah. Opcodes are listed below in hexadecimal with the following symbols. And, we'll just about wrap up with going through these opcodes. 3 N's for the address, 2 N's is an 8-bit constant, 1 N, just, for describing these opcodes down here is a 4-bit constant, X and Y are 4-bit register identifiers, PC is the program counter, I is the 12-bit register for memory address, similar to void pointer, and VN is one of 16 available variables. This is super chip based, as that's the most commonly encountered extension set today. Footnotes denote incompatibilities with original CHIP-8 instruction set. Okay, so the first digit, I guess the most significant, tells you what type of opcode, and then subsequent digits could be, what type of opcode, and then what the operand is, I guess. So call machine code routine at address NNN. That's not really necessary. 2 zeros, and then E0 is for clearing the screen, returning from subroutine. Oh, nice. You got some pseudocode here. Go to address, call subroutine, skip next instruction if equal, so an if statement, whether the VX register is equal to that 8-bit constant. If it's not equal, it skips. Okay, so there's a test for 2 different variables being equal to each other. Setting a variable there, that's kind of interesting. Adding, so like a store plus kind of function. This is interesting. It's kind of reminding me almost of, oh wow, assembly-like, not assembly-like, but the types of commands that I saw on keystroke programmable calculators. Okay, set x vx equal to vy, bitwise or, bitwise and, exclusive or adds vy to vx. That's kind of interesting. So you don't have to keep like loading in, like on the Kenback, loading in numbers to particular memory, to particular registers from a memory location. You can go from variable to variable, memory location to memory location, instead of memory location to register, and register to memory location, so on. Bit shifts, I guess nothing too exciting there. Drawing sprites, bitwise and operation on a random number. That is interesting. Okay. Key press, delay timers. Let's see if I missed anything yet. Display, key operations, timer, another key press, delay timer, sound timer to a particular variable, VX to I, sprite address, I to location of the sprite for character, sets I to the location of the sprite for that character in VX. Okay, interesting. And store binary coded decimal representation of VX. Interesting. Interesting. Okay. Stores from Z0 VX in memory. Starting at address I. Offsets increased by 1 for each value written, but I itself is unmodified. Okay. All right, and that's a quick overview of CHIP-8. In future videos, I'll try this out on the FX9860G2 as well as on a Palm OS device. I hope you enjoyed this video. I hope it was helpful and informational. If you have any thoughts, suggestions, or questions, leave them in the comments down below. And please like and subscribe as always. Thanks so much for watching and have a great one.